Hello, class, and welcome again to week 4, week 5 lecture. This time we're going to talk about ANOVA, or analysis of variance. This is a quick lecture actually because I tried to synthesize all the important components of ANOVA, and I only have 11 slides for this particular topic, so hopefully I don't inundate you with too many theories, and we can move on also to practical applications of all the statistics that we have discussed so far in the last 4 weeks. So let's talk about ANOVA. So what is ANOVA? Well, ANOVA stands for analysis of variance. So think again, we are looking at variance, and remember that variance is a feature of a population. And remember that variance is part of the measures for dispersion. So when you think of ANOVA, because it utilizes or analyzes the variance, well, you need to think then that it is a parametric test. Let's review some basic concepts of ANOVA. Well, ANOVA utilizes the variance, but this time it is the variance of a minimum of 3 population or 3 samples. In the previous weeks, we have learned basic concepts on comparing the variances of 2 populations, and typically we use the F ratio and the F distribution. I haven't covered the F ratio and F distribution, but I think that is something that I'd like you to look it up for yourself, because that is a foundation of ANOVA. But I've already discussed with you what is the z-score distribution, what is a t distribution, and now we're just looking at F distribution. Again, just minor differences, different tables, but ANOVA builds on the F distribution and F ratio. So F ratio is an important concept to remember in the analysis of variance. A quick review: F ratio is a ratio of the 2 variances, but it is a central component of ANOVA. And ANOVA is a quantitative statistical method that moves beyond comparing just 2 populations. Remember, in all of our t-tests, even all of our non-parametric Mann-Whitney test, or our Wilcoxon match pair test, those are all talking about just simply 2 populations. So what happens then if we're interested in the means of 3 or more samples? What are you going to do if you are the statistician? Well, just like Gusset did, you need to create your own test statistics, and that's the beginning of ANOVA. It's called the analysis of variance. This is a statistical method that moves beyond comparing just 2 populations, or just comparing 2 means of a population. ANOVA allows the experimental researcher then to compare multiple populations, subgroups of multiple populations. For example, if you look at your dependent variable as your National Collegiate Entrance Examination score, and then you want to compare the means of the NCEE for 3 different sample, for example, those who took the exam from Mindanao, Luzon, and Visayas. So that's 3. You have 3 sample means if you have 3 subgroups. You cannot do t-test. And you cannot do z-scores. What else? You cannot do independent sample t-test for that particular question, because you are now talking about three subgroups. So it's important to remember that t-tests, they have limitations. They always compare two populations or two means of two populations. So once we start comparing multiple population, that's three populations or more, or three subgroups of multiple populations, then we need to use ANOVA, because ANOVA can also examine the interactions between groups, including their subgroups. So that's the beauty of ANOVA. So for example, I wanted to know what is the whether there is a statistically significant difference in the mean score of NCEE in three samples based on regions, Luzon, Visayas, and Mindanao, among low income, middle income, and high income family members of the test takers. So that is what you call interactions between groups, including their subgroups. So my first three groups were Luzon, Visayas, and Mindanao. And then I have subgroups between those among those three groups. And I wanted to know what is the interaction between the data that I got from Luzon, Visayas, and Mindanao in terms of the mean score of the NCEE, and what is the interaction of the other subgroups that I'm interested, that is based on income, low income, middle income, and high income. Of course, I need to operationally define who are those people that I considered low income. Are those family members whose father and mother income is less than 100,000 pesos, and the middle income are the one that's 101 to 250,000 pesos, and then the high income are the ones with 200. So it's always just 1 point higher than your highest level from the previous level. So if I say less than 100,000 pesos are low income, then 101 to 250 are my middle income, then 251,000 and higher are my high income. So that is, again, you need to operationally define that, but then you create subgroups. So that's your grouping variables, but this time you have a minimum of three groupings for your variables. ANOVA is, again, very, very useful once you start comparing the samples of more than two population. We discussed about the independent sample t-test, the match sample t-test, but those are all having just two means, two populations. T-test we know is too limited. The phenomenon of interest for the experimental researchers are complex nowadays. I'll give you an example. You could be interested in examining inflammatory cytokines with 30 multiplex cytokines, and then you also wanted to look at metabolic biomarkers such as DHEA, serotonin. You can think one more of the metabolic biomarkers, perhaps. Of course, glucocorticosteroids are metabolic biomarkers in older adults versus control groups. So once you create groups of three and subgroups of three, t-test is gone because it has its own limitation. It can only do two, it can only compare two means. So above that, beyond the two population, beyond two means of two populations, you need to move on to ANOVA. So an example when a situation or an experiment where ANOVA is applicable is, suppose I want to compare the means inflammatory and metabolic biomarkers of three samples. I have older adults with cancer-related fatigue, older adults with chronic fatigue syndrome, and older adults with no fatigue, to see if a difference exists somewhere among them. That's where you are going to use ANOVA, or analysis of variance. ANOVA expands what we can do in inferential statistics. It can go beyond comparing the means of two populations, and it can even examine the interaction of your grouping variables and the subgroups within that grouping variable. So here's a good demonstration in terms of the three research questions that ANOVA will answer. The first research question is, do all three means, which is represented by x1, x2, and x3, come from a common population? So yes or no, it will be answered by ANOVA. The second research question is one mean so far away from the other two means, therefore this is likely not a mean representing the same population? So that is checking the differences between the variables. And then the last, or the third research question that ANOVA will answer is, are all three means so far apart, therefore all three means likely come from unique populations? So ANOVA answers a minimum of three research questions. How do we apply ANOVA? Well, ANOVA examines the relative distance between three means, and at the same time it tries to help the experimental researcher also conclude whether they come from the same overall population. ANOVA accounts for the total variance of these means. This is such an important concept in ANOVA. It's all about analysis of variance. That's why it gets its name, ANOVA, analysis of variance. So therefore it accounts for the total variance between groups, intra-group, and among the three groups. So as what was mentioned earlier, ANOVA checks the relative distance between three means. It puts all three means into one common larger distribution, as shown right here, and then it will check for statistical significance, and it will answer the three research questions that I just went through in the past slide. So here in the graph, as you can see, on the left side, you might, by just looking at this, you might immediately say, are the distance between the three means statistically significant, so that you will not think that this mean does not come from one population? Or are these means so distant from each other, or far away from each other, that it definitely comes from each unique population? On the graph on your right side, what it shows you then, that it looks like that the mean of the C sample, or the third sample that's under the notation of C, it looks like that it is too far away from the larger group. And ANOVA will analyze that variance and will give you a test statistics whether you are going to be able to keep whether you're going to be able to answer yes or no to one of the three research questions that ANOVA attempts to answer. So the key concepts again in ANOVA is that the null hypothesis in ANOVA is simply expressed as the mean from population 1 is equal to the mean of the population 2 and also equals to the population of the mean of the population number 3. So the assumption is that these three means come from the same overall population, that there's no difference whatsoever among the three means, whether it's the distance between mu1 to mu2, or the distance of mu2 to mu3, or the distance of mu1 with mu3. ANOVA accounts for the total variance. So always remember that ANOVA accounts for all or the total variance. So it can detect statistically significant differences in the mean, whether it's the distance between mu1 and mu2, or mu2 to mu3, or mu1 to all the way to mu3. Please note that in ANOVA we are not asking whether they are exactly equal. That's a misconception. In ANOVA we are actually asking if each mean likely came from the larger overall population. ANOVA, always remember this, examines the variability among or between the sample means, and that's why it accounts for the total variance. It examines the variability among, which is 3, or between, which is mu1 to mu2, mu2 to mu3, because they're next to each other. So between the sample means of two population. Simultaneously, ANOVA will account for the total variance. So here is a graphic representation of how ANOVA accounts for the total variance. So your blue signifies within, it's analysis of the variance within, and then the red is signified, the red arrow signifies how ANOVA accounts for the variance among. Among is for 3. And so looking at this, you know then that ANOVA accounts for total variance. It accounts for the variance between plus the variance within, and therefore the analysis of variance is a variability ratio. And remember that ANOVA utilizes the F ratio from the F distribution. Some important reminders, or some of the assumptions that you need to make sure you check before you run your ANOVA. The data points must be independent from each other. The distribution must be normal, although some small departure can be accommodated. The variance of the samples are not different, so though some departures are accommodated, and you can do the homogeneity of variance test, and it's part when you run your ANOVA. There's always a section where you want to look at the homogeneity of the variance tests, and that has to be statistically significant so that you don't reject the null hypothesis that there is no difference in the variance of the sample. All individuals must be selected at random from the population, so you have your random sampling again as a requirement or as an assumption, and all individuals must have equal chance of being selected. Sample sizes should be equal as possible, but some differences are allowed. So remember, there's three minimum populations when you do ANOVA, analysis of variance, because if it's just two, then you can simply run your t-test for that. But when there's three uh, means from possibly three different population, and you also want to know the interaction of the subgroup in that particular population, then you have to remember you need to have an equal sample size. Although it says here some minor differences are allowed. Technically, minor just simply means one or two or three. So for example, if you have 25 in one sample, you get 24 in your next, in your one grouping has 25, the other grouping has 24, and the other grouping has 18. That's not really a small difference in the sample size. It says here should be equal as possible. So if you have 25 in one grouping, 25 in the other grouping, maybe the third grouping would be 24. All right. So that is what ANOVA is all about. And if you have any question, feel free to email me, or we can also FaceTime or again Viber by phone.